record. So welcome everybody. This is the fifth session of the second season of the Isogeny Club. And today we have Pierrick Dartois. He is a PhD student at INRIA Bordeaux, and he's starting his PhD already with higher dimensional isogenies, which is an interesting choice. And the topic of today is SQISignHD, which fits well together with some of the previous talks we've had. So we've had Antonin in last season talking about SQISign, Jonathan, of course, 2 sessions ago, and Michael looking for primes, the session before this one. But today it's about SQISignHD, signing with higher dimensional isogenies. So Pierrick, go ahead. We still see the slides. Yeah, okay. Now it should go to full screen.
Okay, thank you very much, Skrine. And does everybody hear me? Okay,
yep, it's loud and clear.
So today, as announced, I will introduce you to SQISignHD to sign with higher dimensional isogenies. This is joint work with Antonin Leroux, Damien Robert, Benjamin Wesolowski, and I would like to acknowledge particularly and thank Luca De Feo for his help all along this project. So first of all, before introducing you to SQISignHD, I will talk a bit about SQISign to remind the basics that will be useful to our presentation. Then get to the main idea of SQISignHD, which is the higher dimensional isogeny representation due to SIDH attacks, and how these ideas can apply to response and verification algorithms in SQISign, and as well how we should adapt the commitment to optimize efficiency in our particular protocol. Finally, I will present a security and performance analysis of SQISignHD. So first of all, let's get to SQISign. As you probably already all know, SQISign is an identification scheme which is transformed into digital signature via fiat channel transform. So we have a public elliptic curve E0, which is basically the curve G equals 1728. Let's say that a prover knows some secret isogeny tau from E0 to EA, which is random in the isogeny graph. And to prove knowledge of this secret isogeny with this public key EA, he will just commit an elliptic curve E1 generated with a secret isogeny psi, and the verifier will change him with phi, which is another isogeny that he will send. And the prover will have to come up with an isogeny from the public key EA to E2, using, of course, the knowledge of his secret without revealing it. So the verifier will just accept this response sigma if he's sure that the prover does not cheated, meaning if the precomposition of a phi dual with sigma is cyclic. So we transform this scheme into a digital signature with fiat Samir transform. So how can we do that? Given a message M, we commit as previously an elliptic curve with the secret isogeny psi, and to generate the challenge, instead of asking the prover, we hash the message and to generate the challenge, and that way we just compute the response sigma and send E1 sigma to the verifier as our signature. The verification is then simply to recompute the hash function, so the hash giving the challenge, and to verify, as previously, that sigma has the right form. So actually, this is an important side remark for efficiency and compactness purposes. In SQISign, the curve E1 doesn't need to be sensed because we can recover it with sigma because it gives E2 and by computing the challenge backwards. But this trick does not apply, unfortunately, to SQISignHD. So this remark will be important when we will talk about compactness. Now, the question is, how can we compute the signature sigma? Actually, we use the well-known direct correspondence between the world of supersingular elliptic curves and the world of quaternions. We associate to any J invariant up to Galois conjugacy, maximal order in the quaternion algebra ramifying at P and infinity, which is just the endomorphism ring, and given an isogeny between two elliptic curves, we associate an ideal, the kernel ideal, which is a left ideal for the endomorphism ring of the domain and the right ideal for the endomorphism ring of the codomain. Two isogenies with the same domain and codomain correspond to equivalent ideals in the quaternion world. The dual corresponds to the conjugates, and the composition corresponds to the multiplication of ideals. If we have an endomorphism, furthermore, it corresponds to the principal ideal generated by these elements. And the degree is, of course, the norm of the kernel ideal. So how do we use it in SQISign? We just know that the ideal that we will find, which is associated to our response, will be just equivalent to this ideal path represented here. And so what we have to find is just an equivalent ideal to this J given by this formula, which is random and which has the good norm. So it has to have power smooth, not power smooth, simply smooth norm, so a power of a prime L, in order to be efficiently translated into an isogeny. We need actually to translate this ideal into the isogeny sigma, so we need the ideal to have smooth norm. For that, we use KLPT, and then we do the ideal to isogeny translation, which is costly, even if it's polynomial, because we need, since we need smooth norm, by KLPT algorithm, we only obtain a very high degree isogenies, so we don't have enough torsion to compute it just once, and we need to compute it piecewise, and this is a very slow process. So that's what we want to improve in SQISignHD, and by going into higher dimension, we achieve to circumvent those difficulties. So I introduced the notion of efficient representation. This is basically what we want to compute for any isogeny. An efficient representation is given by the data of polynomial size representing this isogeny and an algorithm, taking as input this data and a point, and returning the evaluation of that point in polynomial time. So an example is when you have an L to the E isogeny, it can be decomposed into a chain of L isogenies, and it is an efficient representation because we have a simple algorithm. It's just that we evaluate each isogeny in the chain successively to evaluate a point. The state of the art before we knew about attacks against SIDH and higher dimensional isogeny representation is just to get every time we can to this representation that we know. like all efficient representations were essentially equivalent to that one. And for that reason, we could only represent smooth degree isogenies. And so that's the reason why we needed KLPT in SQISign and this costly ideal to isogeny translation. So now we go concretely into higher dimension. And I just recall what is a d-isogeny in general in higher dimension, because it's a bit different from dimension 1. So let's say that we have an isogeny between principally polarized abelian varieties. So that means that the polarization are just isomorphisms between the varieties and their dual. And we denote phi tilde, the analog of the one-dimensional dual, given simply by the composition of the polarization of B, the dual of phi, and the inverse of the polarization of A. And we say that phi is a d-isogeny if phi tilde phi is the scalar multiplication by D. So this property is not always satisfied in higher dimension. Of course, in dimension 1, in between elliptic curves, we always have this property, and D is the degree, but it's not the case always in higher dimension. But what we do have in higher dimension is once we know that we have an L to the E isogeny, we can decompose it as a chain of L isogenies. So we get as well the previous efficient representation that we talked about in dimension 1. But that's not that representation that interests us. It's more what we can do with it. And here comes Canny's lemma. So if we have an AB isogeny diamond, so meaning a diagram like this, where phi and phi prime have degree A, and psi prime have degree B, then we have, if A and B are co-prime to the characteristic, a higher dimensional isogeny from AB prime to BA prime, given by this formula, where all those isogenies are in the diagram. And this is the D isogeny, actually, where D is the sum of A and B. And if A and B are co-prime, we have a simple formula for the kernel. So if we know how to evaluate the D torsion via these isogenies, then we have the kernel, we can compute this isogeny. And since phi, for instance, is just a component of this isogeny in matricial representation, we can evaluate phi everywhere. So that's the powerful idea of Canny's lemma used in SIDH attacks. And we will use it constructively here in SQISignHD. So let's say that we want to represent our sigma, our response or signature of degree Q smaller to L to the I. We have this big sigma, which is just a two-dimensional diagonal isogeny given by sigma. Let A1 and E2 be integers such that the sum of their square is L to the E minus Q. And alpha and alpha prime, those matrices, which are simply, which play the role of the complex number A1 plus A2I, for instance, because their degree is A1 square plus A2 square. So given all those data, we have an isogeny diamond given by this commutative diagram, and it yields an isogeny, an L to the E isogeny of dimension 4, which is just basically an endomorphism. And this endomorphism represents sigma, which is just a component of this matrix here. So we have the formula for the kernel by Canny's lemma, and This formula is very convenient because it means that if we know the image via sigma of the L to the E torsion, then we can evaluate the whole kernel, because like this alpha tilde is just scalar multiplications. And so knowing the kernel, of course, we can compute the isogeny F actually as an L isogeny chain. And knowing F, we can evaluate sigma everywhere, so we have an efficient representation. That's the basic idea of SQISignHD. So the bad news is that to make this representation concrete, we need to go into dimension 4. But the good news is that we get shorter isogenies. Why? Because we have much more freedom on the choice of the degree Q, because we don't need it to be smooth. It can be anything, well, almost anything, we will see. And it can have a norm which is close to the square root of P, which is the optimal norm for an ideal. Whereas in SQISign, the norm were close to P to the 15 out of 4. And so that's way better. Unfortunately, how much freedom do we have on Q? In dimension 4, we have much more freedom, but not all the freedom we want. We still need to be able to find those integers A1 and E2 such that LE minus Q is the sum of those squares. So for that, we need L to the E minus Q to be a prime congruent to 1 modulo 4 to ensure that we can use Kornakia's algorithm and find those A1 and E2 easily. But we couldn't get rid of that condition by going into even higher dimension. So this has just a theoretical interest, just a side remark. If we want to have a perfect distribution, a perfectly random distribution of isogenies, we need to remove this constraint of Q. And so we can do it by going into dimension 8, and it provides actually a better proof of the zero knowledge properties. But concretely, how do we do? We just write L to the E minus Q as a sum of 4 squares. That we can always do it. This is just a standard theorem by Legendre. And now we just slightly different notation, like this diagonal matrix again, and this matrix alpha and this matrix alpha prime, whose degree are the sum of the AI square. We get an isogeny in dimension 8, which embeds sigma. Of course, we won't use this representation because it's not practical, but it has some theoretical interest for security, and we present it as an alternate scheme in our paper. So right now, let's get back to dimension 4 and present the algorithms for response and verification in dimension 4 specifically. So as in SQISign, for the response algorithm, we use the Turing correspondence. So we take an ideal, which is just the path from the secret key, the challenge, the commitment and challenge, this ideal J here, and we find a random equivalent ideal A to J, which has a good norm, so meaning Li minus Q is prime congruent to 1 modulo 4 to be able to represent our isogeny. Then we generate a canonical basis of the L to the E torsion in EA. We evaluate it via sigma, the isogeny associated to I. I will explain how this evaluation is done. And then by sending Q and the evaluation of the basis via sigma, we can compute the isogeny in dimension 4. And that will be the work of the verifier. So right now, we still need to explain how this evaluation of points via sigma is done. What we know is that this isogeny path, like tau, sigma, phi, psi, is just an endomorphism, gamma. And we can compute effectively this endomorphism by just computing the product of the ideals, I tau, I phi, I psi, and so on. And it's a principal ideal, so we simply take a generator in the endomorphism ring of E0, and we can evaluate efficiently this generator because we know the endomorphism ring of E0, and knowing that we can find actually the evaluation of sigma via this formula, provided that the degrees of the secret key, commitment, challenge are coprime with L by simply inverting this integer modulo L to the E, sorry. And so in practice, those degrees of challenge, commitment, and secret key will be coprime with L. Those will be power of some prime L prime. And so we can do this computation. But what needs to be explained right now is how we get all those ideals in those steps, because I did not explain how these ideals are obtained. Of course, we know how to obtain I. We also know how to obtain the ideal of the secret key and commitment that can be computed. But for the challenge, it's just the verifier who sends the isogeny phi and not the ideal associated to it. So the prover still needs to be able to compute this ideal, and he cannot do it without knowing the endomorphism ring of E1. So actually, that's the reason why we need a double isogeny path here. So maybe you wonder why there are two isogeny paths from E0 to E1. That's exactly for that reason. So let's explain how the kernel ideal of the challenge is computed right now. So first, we need the basis of the endomorphism ring of E1, the challenge. To do that, we take a basis of E0 that we know, and we push it through our alternate path from E0 to E1. And this path needs to have degree coprime with the degree of phi in order for the basis to be evaluated on the torsion of d phi, the degree of phi. So that's actually the reason why we needed two paths, because one of them is coprime with the challenge and one of them is not. So right now, once we have our basis, we evaluate it on the kernel of phi and solve some discrete logarithm problems to compute a basis of the ideal. So I don't get into the details explained here. They can be found on the paper, and the algorithm actually is not new. It's due to Antonin Leroux. But basically the ideal is that. Right now, we have an idea of how we can sign, and it gives some constraints on the choice of isogeny degrees, hence some constraints on the choice of the prime. Bottom line is that we can choose a prime which is similar to SIDH. We take P equals C, L to the F, L prime F prime minus 1, where L to the F and L prime F prime are close to square root of P, and C, of course, as small as possible. And so those L and L prime are small primes. So it's exactly as in SIDH. For the size of P, in order to be secure against Delft and Galbraith attack in the isogeny graph, which has complexity square root of P, and to ensure a security level lambda against key recovery attack, we need to take prime of 2 lambda bits at least. So for a NIST security level, NIST 1 security level, here is an example of such a prime. So for degree choices right now, we can, as I explained earlier, select our double isogeny path to the commitment, so that one path is a power of L and another is a power of L prime. And as well, what we do is that all the isogenies of the secret key, the main of the commitment and challenge are powers of L prime, because we need them to be coprime with L to make the isogeny evaluation. And so for the size of these degrees, we take approximately P for the key, the secret key, and the challenge in order to have security level lambda. So mainly it means that the public key and the challenge are random in the isogeny graph. And for the challenge, we only need square root of P, because we need a challenge space of size 2 to the lambda to ensure soundness security of lambda bits. So just what needs to be remembered from this slide, which is a bit technical, is just that with those choices of primes, our isogenies are really easy to compute, because the prime has good smoothness properties. So all the dimension 1 isogeny computations that we need for the signature are much more simple than in SQISign, where we had to evaluate isogenies with degrees that were smooth, but not as smooth than SIDH primes. Right now, I can explain the difficult parts of the algorithm of the protocol, which is the verification. So remember that we are given the integer q, which is the degree of our signature, and as well as the image of some points of L to the E torsion. Now, the verifier wants to compute the higher dimensional isogeny representation. So he will find integers a1 and a2 in Z, such that L to the E minus Q is the sum of those integers, and generates the canonical basis of the L to the E torsion to recover the whole kernel of our higher dimensional isogeny F. And then with the kernel, compute the higher dimensional isogeny as an L isogeny chain. And since this isogeny needs to be an endomorphism, all the verification will end up to just verifying if the domain and the codomain of this higher dimensional isogeny map. So now we have just the basics of our verification algorithm, but let's introduce some important optimization for compactness, which is just dividing the computation of the higher dimensional isogeny in 2. So let's say that F is the product of F1, which is an LE1 isogeny, and F2, which is an LE2 isogeny. Then we have formulas for their kernel, and by simply knowing the image of some torsion, so the L to the F1 torsion, where F1 is just bigger than the exponent E1 and E2, we can actually compute the kernel of F1 and F2 tilde. And the verification is now we verify if the codomain of F1 and the codomain of F2 tilde just match to this abelian variety B right here. So this has some very important advantages. Like the main one is that we need half of the torsion that we needed before. And it gives us some more freedom on the choice of the ideal, so on the choice of Q, because we are not constrained by the accessible L to the F torsion that we have anymore. And furthermore, since we need half the torsion that we needed before, our communications, so the points that we send to the prover and what will be our signature, will be twice as more compact as before. So right now, we just took as a black box the higher dimensional isogeny computation and did everything as if we could easily compute it. So I won't go into too many details into that computation, but I can give you an overview. So the first main idea is that if we have an L to the E isogeny, we can, as in dimension 1, decompose it as an L isogeny chain. And we have a simple formula for the kernel of any of those elements on the chain. So this is very convenient because we can apply well-known techniques in dimension 1 to compute those isogeny chains when only the kernel of the whole isogeny is given. Those techniques were first introduced in the paper by Leroux, Jiao, and Plu in 2011, introducing SIDH. And so the idea is that to compute, let's say that E equals 5, for instance, so to compute all the isogeny chain, we need all those kernels represented at the bottom line of this computation tree. And so we just need an optimal strategy to descend this tree with as little multiplication by L or isogeny evaluation as possible. And we get a complexity of E log E arithmetic operation or isogeny evaluation, actually. So what can we do now for the core part of our algorithm, which is the computation of L isogenies? So since we are in dimension 4, we cannot use easy models like Weierstrass model, of course, or we don't have Jacobian models anymore. So we really need the theta model. And actually, all is detailed in the appendix of our preprint. All those computations are done. So this is really the black box. Right now, I will explain the commitments and key generation. We need some adaptation compared to SQISign to be efficient. So recall that we need a double path from E0 to the commitments and as well and the associated kernel ideals as well. And that those the degree of those isogenies are just the square of the accessible torsion. Recall that this is the accessible torsion that we have. So what we do to do this computation is that we generate an endomorphism ring, in E0 with the right norm, L to the 2F, L prime to the 2F prime, and we factor it two different ways. So the first way is that way, and it's easy with the accessible torsion that we have. And the second way is that way. And to factor the second way, we just push this isogeny θ2 via θ prime 1, getting this isogeny put forward of theta 2 by theta prime 1, and the other one as well, like this, by pushing theta prime 1 via theta 2. And so this is, we have simple formula for the kernel, and by taking their composition, we get the path that we want to the commitment, which will be in the center of the diagram here. And of course, the ideas are easy to evaluate once we know the endomorphism. So right now we can be very happy because we have all the algorithmic building blocks of SQISignHD. We have the response, verification, commitment. The key generation is basically derived from the commitment because we need the same degree and also the associated kernel ideal. And just the challenge is the computation of a random isogeny path. So it's not very difficult to compute. So now we can introduce the security analysis of SQISignHD with this construction. So recall that the digital signature that we have is obtained via Fiat-Shamir transform. And so by Fiat-Shamir, we get a secure signature, namely universally unforgeable under chosen message attacks in the random oracle model if it is complete, meaning if the protocol is well constructed. So we did everything for it to be well constructed. Sound, meaning that an attacker cannot guess a response, and zero knowledge, meaning that the response does not leak any information on the secret key. So we will present the last two properties, soundness and zero knowledge, and see why is it sound and zero knowledge. So the soundness argument of SQISignHD is quite similar to SQISign. It's a special soundness argument. Under the hypothesis of Q being coprime with L prime, then given two transcripts for the protocol with the same commitment E1, but different challenges phi prime, then we can extract a witness for a hard relation, meaning that we can extract an endomorphism of EA, which is not scalar, of course. So the idea is just to extract sigma and sigma prime, just the response isogenies from their representations given in the response of the transcripts, and to get this pre-composition, post-composition with the challenges here, it gives a non-scalar endomorphism. So now we present the zero knowledge. So for the zero knowledge, we need to introduce an oracle actually to make the protocol simulatable. So we say that an integer is good if it has, like, if it satisfies our constraints for Q, like just LE to the minus Q is prime congruent to 1 modulo 4, and of course coprime with L prime for soundness reason. And the oracle, random uniform good degree isogeny oracle, RUGDUO, is just an oracle taking on input a supersingular elliptic curve and outputting an efficient representation of an isogeny which has good degree and is sufficiently random for E prime, the codomain, to be randomly uniform in the supersingular isogeny graph, and for the distribution of sigma, the conditional distribution given E and E prime to be uniform among good degree isogenies from E to E prime. So with this oracle, with access to this oracle, and also another heuristic assumption like just E1 to be computationally close to uniform, we get that SQISignHD is computationally honest verifier zero knowledge. So meaning that we can simulate transcripts without using the secret key. with the same distribution as the protocol, or at least computationally indistinguishable distribution. So the simulator, of course, uses the oracle to get a representation of an isogeny which has the same distribution as in the protocol. The oracle was just designed for that. And then we generate a challenge just backwards from E2 to E1, just randomly. And what we get, the output we get, is just similar to a transcript from the protocol, because the representation of the isogeny has the same distribution. Phi is as random as the real challenges. And well, E1 is uniform in the isogeny graph, but we assume that the output commitments in the protocol are computationally close to uniform. So this is indistinguishable from real protocol transcripts. So this is what we get with SQISignHD. We get zero knowledge property under two heuristic assumptions, the oracle and the computational indistinguishability with the uniform of the G invariant of the commitment. Whereas in SQISign, we need a much stronger heuristic hypothesis to be zero knowledge. We need the distribution of the whole signature to be computationally indistinguishable from a random isogeny of fixed degree L to the E. And so if we reveal a whole isogeny, or if we reveal simply a J invariant, well, it looks like it's much more easy to attack the zero knowledge property for SQISign, because this sigma gives much more information. Of course, we have this additional heuristics, which is just an oracle, but this is not a big deal, because with this oracle, actually, we cannot hamper the security of the soundness, for instance, because this oracle cannot be used in existing attacks against the endomorphism ring problem, for instance, that is necessary for soundness. Because actually those attacks don't make any hypothesis on the smoothness of the degree or other properties like that. So of course, we can do even better from a security point of view. We trust the security of SQISignHD, but if we want an even better proof from a theoretical point of view, and if we don't care about making the protocol practical, we can go to dimension 8. In dimension 8, the only heuristic assumption that we need is the access to another oracle, which is simpler than the oracle we introduced earlier. So it's called the radio for random any degree isogeny oracle. So the name is very unexpected. I'm sorry for that. And it takes an input, as input an elliptic curve, which is simple singular, and it sends an efficient representation of an isogeny, which is uniformly random among isogeny of degree at most L to the E. So this oracle is less ad hoc and simpler than the previous one. And so this was the interest of going into dimension 8. And since we don't care about making it practical in dimension 8, we can use inefficient algorithms which are still polynomial time, but not as efficient as the previous ones, for the generation of the commitments. And with those algorithms, we get rid of the heuristic assumption on E1, actually. So now that we trust the security of SQISignHD, we can present some performance results. So I'm very happy to announce that we broke our record for compactness of our signatures in SQISignHD, because to recall, what we need in SQISign for the signature is just an isogeny of degree close to p to the 15th out of 4. And in SQISignHD, we need all this data, but it's just a J invariant with a Q and the image of some points. And since we optimized the representation of those points and also the torsion that we needed, what we get when we sum up the sizes is a signature of size 13 out of 4 log p in SQISignHD, whereas we had an asymptotic size of 15 out of 4 log p in SQISign. So for NIST1 security level, for instance, we are 20% more compact in SQISignHD than in SQISign. So now time efficiency. Of course, with the optimization that we made, the signature is way faster than previously, because the one-dimensional isogenies are way faster to compute with the primes that we chose. Evaluating the isogeny sigma is fast as well. So the preliminary implementation of the signature that we have is way faster than SQISign, but it's still a work in progress, so we don't output timings. On the contrary, in SQISign, we call that we need this costly ideal to isogeny translation, involving a piecewise computation of the isogeny sigma with 30 T isogenies, where T is a power smooth integer close to p to the 5/4, but which is less smooth than the integers that we had in SQISignHD. So the drawback now is not the signature, but of course the verification, because we need to compute isogenies in dimension 4. We have, of course, known algorithms presented in the appendix of our preprint, but those algorithms still need to be implemented to make sure that we have interesting timings. So now a few words of conclusions. From a security point of view, we achieved much better heuristics in SQISignHD. The choice of the prime is also simpler because it's SIDH primes basically. So those primes scale very well, whereas in SQISign, the sieving of those primes were very hard, and actually they are still an open question. And if I'm not wrong, it was even evoked in the previous episode of the Isogeny Club. The signature as well is much more efficient, as we previously said, at the expense maybe of the verification, but not that the isogenies in dimension 4 that we have are way shorter than the isogenies in dimension 1 that we needed to compute in SQISign. So I thank you for your attention. You can find our preprint on that URL address, and I'm happy to answer all the questions that we might have.
Thank you very much, Pierrick, and again, congratulations on what I think is a very fantastic paper and a great result. I guess a question that I have, like, doing a bit, since I'm at RWC, I'll ask an RWC type of question. So for implementers who want to like look at this scheme and implement it, do you think it's actually like more complicated or less complicated than the usual SQISign? Because of course you need more theory of higher dimensional abelian varieties, but also you don't need this small isogeny from L star algorithm, which is kind of convoluted in the original SQISign paper, I guess. So do you have any feeling for this, like, or any opinion here?
Well, from my point of view, implementing the signature is way easier because it involves less heavy computations, and so the algorithms are simpler. Those are just those what I explained. While going into dimension 4 isogenies for the verification, of course, involves a lot of theory on theta model, and actually I'm still learning that part. But what I can tell is that the formulas in the theta model are quite simple to implement. The problem is just that you need to optimize it, to optimize them, and you can use formulas in the appendix of our preprints, and those are not complicated formulas. So if you want a straightforward implementation, I guess you can get it not so hardly. But if you want really to come up with an optimized implementation, I guess more knowledge on the theta model is involved.
Yeah, interesting. Thanks. Looks like there's also a question from the chat. So Thomas Decru asks, do you have any idea whatsoever for the verification time, practical or theoretical?
So practically, from there is a complexity estimate in the appendix on the number of arithmetic operations over FP2 involved to compute the isogeny in dimension 4. And actually, it's comparable to what needed to be done for the signature previously. It's a rough estimate, and it's still not optimized at all. So I guess that we can do much better, and that there will be optimizations, and that we can get, I guess, better timings.
And on this topic, I actually also have another question. So with regards to this performance, can you sort of use a lot of these optimizations we have already for SIDH because you work over a similarly shaped field?
So what kind of optimizations do you need? Do you mention like those on the field arithmetics mainly? You mean, or really high level isogeny computation? What do you mean exactly?
Yeah, I was thinking of field arithmetic, but maybe also for this signature you publish the torsion points, and I think also in SIDH you have some compression tricks there. So maybe in general, actually. Yeah,
we use those optimizations actually. So to get compact signatures, like represent, for instance, the points by simply integers, and like this if we fix a canonical basis, we can by knowledge of these integers find easily the right basis, and also field arithmetics. Of course, since we have SIDH primes, we can use those optimized field arithmetics. So a lot of optimizations do apply actually. So, and even in dimension 4 field arithmetics, those are just basic operations over FP2. So if FP2 computations are faster, then everything is faster.
Cool, thank you. I see at the moment no other questions in the chat. If you still have one question, then you need to type maybe quite quickly.
I have a quick question. So the degree of the signature in isogeny is part of the signature, right? This Q.
Sorry, I didn't get your point.
Sorry, was Q was part of the signature? This degree of the signature isogeny?
Yes.
Okay. Wait. Yeah, no, never mind. This is the question was nonsensical. I would like to take it back.
Yeah, but you know, when we wrote, we just asked ourselves how much information we needed, and we tried really to optimize the signature. So maybe the question you came up with, we already came up with.
Yeah. It felt like maybe you could avoid this somehow, or maybe do something else. But
well, anyway, if you look at the sizes, like this is just half log log p. So it's not that
true. It's quite small.
Like the biggest part is the J invariant. Like really, if you could get rid of the J invariant, it will be incredible. But I guess it's not possible.
No, yeah. No, but yeah, thanks a lot for the talk. Sorry, Klein, I kind of cut you off.
No. It was very good, because in the meantime, Luciano managed to type a question in the chat. So he said, "Thanks for the great talk. At a certain point, you mentioned some kind of optimal strategies to compute a chain of L isogenies between abelian varieties. Is there any known way to compute optimal strategies?"
I guess that for that, we really need concrete implementations for the multiplication by L. Because, well, of course, like to get down, to get bottom left on this computational tree, it's multiplication by L, and to get on the right of the tree, it's just L isogeny evaluation. And to get optimal strategies, we need to precisely compute the complexity of each one of those operations. And once we have done that, then we find the right balance between how many L multiplication and L isogeny evaluations we need. So it's really dependent on the optimizations of the really basic operations that we need. And the strategy for finding optimal strategies is then similar to what we know for SIDH.
Thank you. Luciana, I think that's clear. He says thanks. I think with that, we will stop the recording if there are no last questions.